Welcome viewers, welcome to the new lesson from Dr. R's Biology. If you did not subscribe the channel, you can just click on the subscribe button and bell icon.
Dear students, in the previous video, that is Unit 4, Topic 4, Krebs cycle Part A, we have discussed the reactions of Krebs cycle till the formation of succinyl coenzyme A. That means till the glucose is completely oxidized to carbon dioxide. Now in this session, that is Part B, we will be discussing about the retrieval of oxaloacetate from succinyl coenzyme A, the second part of the Krebs cycle. After that, the Part C video will be discussing the energy balance sheet of Krebs cycle. So now you can just watch the retrieval of oxaloacetate.
Okay, so now let us see what happens to this succinyl coenzyme A. So next reaction. So make sure that you are drawing this in this way with a different color and also that you will understand what is happening. Okay, so now succinyl coenzyme A. This succinyl coenzyme A will be just cleaved by water. So addition of water, hydrolytic cleavage of succinyl coenzyme A will be happening. And as a result, what will happen? There will be release of energy. When there is release of energy, that should be utilized or that should be stored. Here the release of energy is not stored. In this particular step, acetyl coenzyme A and oxaloacetate, that energy is utilized for combining both and forming citrate. Hope you remember citrates in this, that concept I have told. Okay, here there is no combination of molecule and all happening. As a result, this particular energy that is released will be utilized for combining GDP and PI, okay, to form the GTP. So succinyl coenzyme A will be converted into succinic acid or succinate. Okay, succinate. So hydrolytic cleavage is happening. From the name itself, we can see that hydrolytic cleavage. I am just adding that particular water molecule. Hydrolytic cleavage is happening. Okay, so H2O will be entering, and CoA will be released out. Hydrolytic removal. And where the remaining OH of H2O will be. Let us see that. But this particular cleavage will be releasing energy, then that energy will be utilized to combine PI plus GDP, and this will be just released as GTP. Okay. Now there is another continuation process where this GTP will be combining with the ADP. So GTP plus ADP will be resulting in the formation of, so I am just writing in this way, it will be again coming back as GDP and it will be resulting as ATP. Okay, so GTP will be formed and that GTP will be entering with the ADP. As a result, what will be happening? ATP and the GDP will be formed. So this happens. That's why ultimately the product is ATP only, even though we are just forming GTP, representing GTP here. Make sure that this particular reaction, I am just representing here once more, GTP is formed. That will be combining with the ADP. And as a result, what will happen? We can just represent the reaction like this. GDP will be formed and ATP will be formed. And ultimately we can say that ATP is formed. Clear? So this is the process that is happening there. Okay. So who will be the enzyme? Which enzyme will be there? So let us see the resulting molecule and then we can see what will be the enzyme. So what is formed? The succinate will be formed. Succinyl coenzyme A removed the coenzyme A part, and as a result succinyl coenzyme A is formed. C double bond O, CH2, CH2, COO minus. So we can see that this OH is coming here. This OH is coming here. As a result, this happened. Now, what exactly happened here? What happened exactly? Actually, think about the reverse reaction where one GTP molecule is really utilized to add coenzyme A to the succinate to form the succinyl coenzyme A. So succinyl coenzyme A synthesis happened with the utilization of nucleotide triphosphate. Then if nucleotide triphosphate are utilized, the synthesis enzyme is known as synthetase or synthase. We have you told in this way. It is synthetase. So what will be enzyme? Succinyl coenzyme A synthetase is the enzyme. Succinyl coenzyme A synthetase. So that will be the enzyme which will be resulting in the formation of succinate or succinic acid. Hope you got this particular step. Now we are just moving into the next step where the succinate will be converted into fumarate by the enzyme succinate dehydrogenase. Okay, clear? Make sure that you have done this particular structure. I am just erasing this part only. But ensure that you are, I am repeatedly saying, you are taking it in the cyclic form. So the succinate is now undergoing a redox reaction where the succinate will be undergoing an oxidation process. So oxidation process means an oxidizing agent. Who will be the oxidizing agent? So far you have learned about the NADH plus or NAD plus as the oxidizing agent. Here the energy state of succinate is not sufficient to produce, not sufficient to reduce NAD plus into NADH plus H plus. Energy state is comparatively lesser. As a result, we have learned about high energy nucleotides. What will be the, if lesser energy is there, we can see that it is nothing but FAD plus. Sorry, FAD only, not FAD plus. FAD will be the oxidizing agent which oxidizes the succinate to fumarate, where FAD undergo reduction and it will be forming FADH2. Okay, so that is happening here. So we will be just seeing that particular thing. Succinate is undergoing oxidation process. This hydrogen and this hydrogen will be removed. Okay, so we can see here. I'm just writing with a FAD blue, FAD, and FAD will be entering, and as a result, what will be formed? FADH, sorry, this H should be blank because you can see that this hydrogen and this hydrogen is coming. FADH2, FADH2 is formed. But there is another important thing that you have to keep in mind. This FADH2 will not be retained as FADH2. Instead, it will be just soon after the formation, it will be just getting oxidized and it will be just entering into the oxidative phosphorylation process. So we can just see that this FADH2 will be again coming back to FAD. So now where this H2 and 2 E minus will be going, the two electrons, okay, and 2 proton will be just entering into oxidative phosphorylation. We will be seeing here that in the oxidative phosphorylation part, oxidative phosphorylation. Okay, so we can see that the enzyme that catalyzes this reaction, which is known as the succinate dehydrogenase, is nothing but the complex that is present in the electron transport chain that we will be learning later. So electron transport, it is actually entering in the electron transport chain, and through oxidative phosphorylation this will be taking place in the formation of ATP. Okay, so soon after the formation of FADH2, it will be undergoing oxidation to release electron and hydrogen and coming back as the FAD. Now what is the remaining thing? Actually nothing is there. So we can just see the COOH, CH, COO minus. So what will be there in between? There will be the formation of double bond, because this carbon is losing one bond with the hydrogen and this carbon is also losing one bond with the hydrogen. As a result, both will be sharing that particular bond. So in between this carbon and this carbon, there will be formation of double bond. So let us see the part. So C double bond O. I'm just making it as the COO minus, because in this particular thing we have represented to C, the water OH is added. So I'm just making it COO minus. Now CH double bond CH, then COO minus. This is fumarate. So fumarate is that. Okay, now we can see the play by the enzyme lyase. Okay, lyase enzyme, because we have learned in the lyase class of enzyme one example, that is fumarate is converted into malate, where the malate don't have this particular double bond and fumarate have this particular double bond. So removal of double bond by addition of a molecule, it is known as the lyase enzyme. So lyase class of enzyme will be playing a role in the next step. So let us see that particular step. Okay, so hope you noted all these reactions. So remember about this particular thing, FADH2 is directly entering into the electron transport chain. The question will be coming why? Because the enzyme that catalyzes this particular reaction, succinate dehydrogenase, is actually the part of electron transport chain. That's why it is directly entering. On the other hand, NADH2 is not directly entering. Instead, it will be forming here and then it will be going to enter the electron transport chain. Because the complex which is receiving electron from NADH2 is other than the enzyme that is forming the NADH2. Okay, NADH plus H plus. So let us see the conversion of fumarate to malate. So this is the second last step of the Krebs cycle. So I am just adding water. So H2O will be added. Okay. And as a result, where it will be added, one here and one there. Okay, so you can see here, black one, COO minus. Okay, CH, I will be adding later, and then CH, COO minus. So you can see the malate here, OH. So OH is coming from here, and NH is coming here. Okay, COO minus, CHOH, CHH, and then CO minus. A dicarboxylic acid is coming. Clear? So now, what should be what is the enzyme? It is fumarase enzyme, fumarase, which comes under the lyase class, where we can see the double bond between these two is removed. Okay. Now we can see another reaction. Okay. So there you can see the oxidation will be happening to this particular malate. Oxidation is happening to this particular malate. That is the last step of Krebs cycle by which the oxaloacetate is retrieved. So you can see that particular thing. I'm just drawing it in this particular direction. Okay, fumarate to malate conversion by the enzyme fumarase by the addition of water. So there is dehydrogenation or the oxidation of malate is happening to, which will be resulting in the formation of oxaloacetate. So we can see here. I'm just drawing it in this direction. Now we know that the COO minus, it is undergoing, I told you, oxidation. So what will be happening? We know that a keto acid, keto dicarboxylic acid is actually this oxaloacetate. So this particular hydrogen and this particular hydrogen will be removed. So we can see that there will be C double bond O. Okay. And so this hydrogen and this hydrogen is removed. So what will be there? So NAD plus will be just converted into NADH, this particular H, plus H plus this particular H. Okay, what is the enzyme? Malate dehydrogenase. Redox reaction. Where NAD plus is undergoing reduction, malate is undergoing oxidation. So after removing this H and this H, what is remaining? The C double bond O. And now the remaining part C H H and then CO minus. So there comes the oxaloacetate. So we have retrieved oxaloacetate that entered into the Krebs cycle in the first reaction, where it combined with the acetyl coenzyme A formed the citrate. So that here by this particular step the Krebs cycle ends. Okay. So after this video, after this lesson, you have to watch the energy balance sheet of Krebs cycle. Okay, so you have to watch that particular thing, then only you will be familiar. So what should be remembered in this particular Krebs cycle? First step of Krebs cycle, the union of acetyl coenzyme A and the union of acetyl coenzyme A. Some monkeys are going out. I don't know why. Okay, union of acetyl coenzyme A plus oxaloacetate and forming citrate. Citrate is dicarboxylic acid. Citrate is the first product. Okay, tricarboxylic acid and citrate is the first product. And it is catalyzed by synthase enzyme. It is known as synthase because no nucleotide triphosphate is involved. Instead, the power, the energy that is released due to removal of coenzyme A from the acetyl coenzyme A is utilized for combining both molecule oxaloacetate and acetate part of the acetyl coenzyme A into citrate. Now the citrate is converted into isocitrate, isomerization process, where water is removed and then added. Now isocitrate is oxidatively decarboxylated into alpha ketoglutarate, then alpha ketoglutarate to succinyl coenzyme A, another oxidative decarboxylation. By this particular step, glucose oxidation is complete. Now after that, every step is actually the process of retrieval of the oxaloacetate which took part in the first step. Now the succinyl coenzyme A will be converted into succinate. Succinate is then converted into fumarate. Fumarate is then converted into malate, and then malate is undergoing oxidation to form the oxaloacetate. So where we can see the reduction process and oxidation process, removal of CO2 in the Linger reaction, conversion of isocitrate to glutarate, then alpha ketoglutarate to succinyl coenzyme A. So these are the three reactions where you can find the removal of carbon dioxide. What are the reactions where you can find the formation of NADH plus H plus? You can see in case of the Linger reaction, and then in case of the isocitrate to alpha ketoglutarate, then alpha ketoglutarate to succinyl coenzyme A, then malate to oxaloacetate. Then where you can find FADH2 formation? So it is nothing but there in the succinate dehydrogenase, that means succinate to fumarate part. And where you can find the formation of GTP? The GTP storage is coming from the energy that is released due to removal of coenzyme A from the succinyl coenzyme A. So succinyl coenzyme A to succinate is actually the GTP removing step. So that's about the Krebs cycle. Ensure that you are learning in this way by understanding what is happening, by understanding which molecules are interacting, and by understanding what are the energy released, in which form the glucose is completely getting oxidized, in which step that is happening, etc. Hope you enjoy the lesson, you understood the concept well, and thank you. If you have any doubt, you have to ask. It can be through the comment box. Okay, thank you.